Okay, so as I told you that we will start with this operator precedence parser first. I mean, we will introduce the bottom-up parser over here, and we have to go through this operator precedence parser and all the LR parsers one by one. So let's start the topic. That is operator precedence parser. So you see, uh, the reason for name, I mean this particular name operator precedence parser is that it is mainly used for defining different mathematical operators in the compiler. I mean, okay, so the first term that we have to introduce here, regarding the operator precedence parser, is called operator grammar. Okay. So what is operator grammar? The grammar used to define the mathematical operations is called operator grammar. Okay, now if we want to work with this operator precedence parser, I mean, in case of operator grammar, obviously we have to design operator grammar, and remember there is some restrictions present in this operator grammar, so we have to understand the restriction first. I mean, we have to remember the restriction, or I mean, clearly, and then only we can proceed. Okay, so for example, uh, let's take example number one. Okay, example number one. Suppose that I have written something like E2 E plus E or or I. So this is very natural, right? Any particular any string with multiplication and addition can be expressed. I mean, any mathematical expression with multiplication and addition is expressed can be expressed by this grammar, right? Now this is what I can say an operator grammar. This is an operator grammar. Now question, why is I'm saying this? It does not mean that, I mean, it's not only because that I can generate any mathematical equation with plus and minus, plus and multiplication. There is one more reason. Let me write it. So the reason is that no two variables are adjacent. This is reason number one. Another reason there is that there is no lambda production. So if you find there is a lambda production in a particular grammar, it's not possible to design a operator precedence parser using that lambda production. In that case, you have to remove that lambda production, maybe, and if you want to remove that, definitely maybe you have to introduce some more production rules in the grammar, but there should not have any lambda production in any operator grammar. So that means naturally, if I say that if I have a grammar something like this, E A E, okay, or maybe ID, and now this A can be I mean uh, plus or star. Basically, what I have written, I've written the same grammar, right? Just in place of A, I can have plus or I can have a star. But this is not an operator grammar. Although both production rules will generate same string at the end, but because of this particular grammar, production rule is not following this reason number 1, that's why it is not an operator grammar. If you want to make it operator grammar, you have to convert, you have to replace this A by the other terminals that is represented here. Okay. Now, one more thing you can say that E to E plus E, E star E, ID, this is an ambiguous grammar, right? It's an ambiguous grammar. With respect to when we understood what an ambiguous grammar is, we had an example like this. And one thing I told you, if you recall, that ambiguity should be removed from a grammar before we start a parser design. But I hope you can recall more. One more thing I have told you, that is, there is only one exception which can work with an ambiguous grammar, and that is what this operator precedence parser. Operator precedence parser does not require an unambiguous grammar to parse it. Now see why it is. The reason is that you see this why this ambiguity came. This ambiguity came because of the plus and star which will work first is not defined somehow in this grammar, right? And that is the problem of confusion. That is the root of the confusion, and that's why we say it is ambiguous. Now, in case of operator precedence parser, what we have a table, what we call operation relation table, and in this operation relation table, it is clearly defined for a particular grammar of a language. There is an operator relation table in case of operator precedence parser, and in the operator relation table, it is clearly defined that which particular terminal has terminal is have more precedence than which other terminals, or maybe lesser precedence. Now, since this precedence is defined, and that's why this confusion can be nullified over here. So for example, if we draw a operator relation table for a grammar something like that, just I have discussed here, let's write it here again. So the grammar is E2 E plus E, or E star E, or ID. right? Now remember, in the operator relation table we don't have any non-terminals. It's built up of only the terminals. So let's draw it first. So first of all, how many terminals are present? Plus and star. By the way, I had a mistake. Not only terminals, but also there is one more thing present, that is what we call dollar, because dollar present at the end of the string. So dollar should be associated. Now I have three terminals here, ID, plus and star and dollar. So that means there will be 4 rows and 4 columns, as simple as that. So that means let's draw a table first. Four row. So just a minute. And so these are representing your ID. This is representing your ID. Uh, this is say plus. This is say star, and this is dollar. Okay, in this side also ID plus star in the same order you have to write. Okay. Now we have you must remember something, some rules over here. For example, for example, always remember that always remember that some points are very important points actually. Identifier has higher precedence than any mathematical operator. Okay, this is point number one. Uh, that mean this ID is the precedence of ID is greater than plus star, you know, even dollar. Okay. Now you see, there is one more thing, that is you can decide yourself in your side according to your grammar that for other cases, for example with respect to plus and star, which will have higher precedence. Obviously you will say that star will have higher precedence of plus. Yes, that's true. But if you want to design your grammar such that plus will have higher precedence than star, then you can do that, because it is deterministically defined in this particular table that which particular operator has higher precedence than which other operators. As simple as that. Now if I want to write, if I just just try to write which is higher than which one, obviously ID to ID is not you know it's not possible, because two ID cannot be side by side. Two ID, I mean two identifiers should be you know I mean, between two identifier, you must have a plus or star, any other operator, right? So that means if two identifier come, you don't, there is no, I mean, it's not a place to decide that which identifier will work first, like that. Now, since ID is greater than any other operator, so that means definitely for the other cases it is greater than, right? Now, plus to ID, plus is lesser than ID. Question is that what about plus to plus? Remember one thing, that I can write, I can write plus to plus here. I mean, let's write it here. Just writing it. That I'm writing, say, plus is greater than plus. What does it mean? It means that plus is left associative. Why I am saying this? Just assume that this plus you have in this side, in the left side, in the right side you have the plus that is on the column, and among these two pluses, which pluses you are giving priority? You are giving priority whatever in the left side. That means plus is left associative. If you want your plus should be right associative, then plus to plus should have a lesser than sign over here. Okay, so just for in my case, in my case I'm taking that plus is left associative. That means that's why I'm giving plus is greater than this plus. Okay, and obviously plus should be lesser than this star, and plus should be greater than the dollar. By the way, always remember one thing, just like identifier has the higher precedence, um, higher precedence than um, mm, I mean than any other operator. In the same way, you should also remember that dollar has lower precedence than any other operator. Okay, these two things is very vital. Please remember these two points. If you somehow had a mistake over here, your operator design, I mean operator parser design will be wrong. Okay. Anyway, so let's proceed. Like star with ID. Obviously, star is lesser than ID because we know ID has the highest precedence. And star with plus. Obviously, star is greater than plus. But star with star, here the same thing again. So I can again consider that star is also left associative. That means star is greater than this star. Okay, and star is greater than also this dollar. So you see, with respect to dollar, everything is greater than dollar, right? And with respect to this dollar, everything should be lesser than. I mean dollar is lesser than to every other. And obviously dollar cannot be compared with dollar, just like ID cannot be compared with ID. So this is what I can say an operator, a probable operator relation table for a grammar like what we have here, E to E plus E or E star E or ID. Okay. Now question is that how to parse this. So we have some parsing rule. Okay, we have some parsing rule. So you have to note that parsing rule. So every parser has its own rule. This particular parser has also its own rule. But remember one thing, that like you have seen in case of LL1 parser, we have a stack. In the same way, in an operator precedence parser also we have a stack. Okay. And let's write the rule here. So definitely if stack is there, we will have something on the top of the stack every time, right? So let's write it. Rule number one. Rule number one is top of the stack is less than equal to look ahead. It may happen, right? So in that case, this is what to do. I will write it. And the second point is, the second thing can be, since it is less than equal to, the second option can be obviously top of the stack is greater than look ahead. As simple as that, right? Other than there is not, nothing is possible. So if it is lesser than equal to look ahead, so what to do? You have to do two things. Number one, push the look ahead into the stack. Into the stack. And number two, increment the look ahead pointer. Okay. And in case of if it is greater than look ahead, then what we'll do, we have simple thing, that is pop from stack. As simple as that, nothing to do. And during popping, actually, when we will do some example, you will see that during popping we will realize that what is the particular production rule that you require to reduce from the string. Remember one thing, that we are now discussing about top down parser. That means, like in previous case, in case of LL1 parser, what we have seen, let's see. In case of LL1 parser, what you have seen? Through the LL1 parsing table, we have seen that we started with here, and one by one we realized that what are the production rules. We started from a particular, non-terminal S. We started from this S, and we found using this particular using this particular method, that whether I have to use S2 opening this particular production rule, or should I use S2 lambda. That we have decided with this particular technique, right? So we started from the start symbol, S, and we ended at this particular string. So that's why it was top down parser. We started from top and going toward downwards. But now what you are doing, you are actually working with bottom up parser. That means we will start from the string, and as the look ahead will go till the end, we will realize that what are the production rules that I should use in which order, so that I can, from the string I can generate the parse tree till the start symbol. So the direction of generating the parse tree is totally opposite, right? And that's why this pop will, when you will see an example, I hope it will be much more clear that when the pop, you will do the pop from the stack, that mean basically you are reducing the non-terminal to its immediate, sorry, you are reducing the terminal symbols, I mean the characters of the string, to immediate non-terminals, and maybe even more in the level above, to generate that particular start symbol. I mean the tree will be generated. So ultimately, whatever the person may be, the ultimate job is to check whether the string is correct or not. Now some parser checking from start symbol is generating the string or not, and some parser is checking from the string I can generate the parse tree or not. And this is what actually you are going the second option. So that's why you call bottom up parser. Even in case of LR parser also in future, you will see we will go for bottom up. That those are all bottom up parser. That means we will start from string and we will generate the parse tree towards the start symbol. So now we have to see an example.